Hello everyone. In this video I'll be explaining the Chinese remainder theorem. Uh, so I begin first by explaining some system that was explained in the concrete mathematics book in section 4.7. Let's say if we have n mod at 15. We also examine the values like n mod 3 and n mod 5. So here we can find the table. We go through all the numbers. Okay. 9, 10. This we go 0, 1, 2, 0, 1, 2, and 2, and so on. This we go 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and 0, and so on until after the 15th row. So when this value is equal to 14, then we start to have repetition again from 0, 0. So here we can somehow see that this pair here corresponds to some number here. So each unique number from this in this list corresponds to exactly a unique pair from here. And the pairs here are not repeated. So yeah, this is one. It was, I think, the residual system, something like that. So here we can even extend this even more. So we can have, let's say, n mod 30, and then we would go to all its divisors like that. N mod 2, N mod 3, N mod 5. Basically find that each number here, let's say something like 11, will correspond to one triple here. Yeah, so it should be something like 1. And basically this triple will, like, there will be one-to-one correspondence between the 11 and this triple. So here we have like all triples, so this can have two options, times 3 times 5, which is equal to 30, which is the same number here. Basically each of these triples will correspond to one number from here. We can look in something, let's say mod 4 and mod 6. In this mod 12, 0, 1, 2, 3, 5, 6, 7, 8, 9, 10, 11. This is 1, 2, 3, 1, 2, and this will be 0, 1, 2, 3, 4, 5. Basically here we have this pair 0, 0, there is 1, 1, 2, 2, 3, 3, 2, 4, 1, 5, and so on. So it still is the same system here. And here it only happens because this 12 is the LCM of the 4 and 6. 2 times 4. This corresponds to the 10, so on. So this has to be like this because we can't have all the possibilities of, from here times all the possibilities from here. So this is the residual space of this 12 and the corresponding 4 and 6. So basically we also have here like each pair corresponds to one of the numbers here, like a one-to-one correspondence. So we'd like to solve some problem that basically once we have and say A mod n, we basically transform it to E1 and N1. And mod A mod n. So somehow we want to make this transformation in both directions. And here we have to have the condition that the LCM of these n's here, n1, nk, and so on, till nk. So all of this is equal to n. So here we have all of these numbers are divisors of n. So the transformation in this direction is pretty easy. So basically, if we have A is congruent let's say that, so yeah, this number is equal or the sum multiple of n. Where r here is so the remainder of like A divided by n, or the, let's say, the smallest positive integer that is equivalent to A. Here from this we have also that if we take this equation modulo n, like n1 or any of these n's, it should still remain the same because A is congruent to R and Ni. And basically this part is divisible by Ni, so you can, so this part is equivalent to 0. That's why we still have this. So whenever we plug A here, we can basically get the remainder using all the n's here, and we will have the corresponding triplet or tuple. So basically this is how we make this transformation. And about the other direction, so if we have this tuple and we want to get back this from it. How do we do that? So this is done using what's called Chinese remainder theorem. So I will explain how to do it on two equations first, and then we can try to generalize it on that. So we begin saying that we have some x, which is congruent to a1 mod n1, and e2 mod n2. Well, most of the literature I actually found has the assumption that n1 and n2 are co-primes. Here I will not make this assumption, and I will still attempt to solve the Chinese remainder theorem. Yeah, the first time I saw this solution, there was some equation in Wikipedia, so this is where I got the idea, but then somehow I couldn't find it anymore. So I'll begin here by so to solve this by using the definition of the modular here. So we have that 1 is equal to 1 and 1, which is also equal to a2 as a2 and 2. So basically, this is like this part comes from the first equation, this comes from the second equation. So here we can reorder these two parts here. So we have like k1 times n1 minus k2 times n2. This is equal to e2 minus a1. I'll just copy this part here. This is like what we have so far from the equations of the third that we have. Here we can try to solve this from the using Bezout's identity. So we can get some coefficient A and B such that this is true. So here here we multiply. So assuming we use the Bezout's identity to get this, we multiply this by this value 2 over e1 and this CCD. So after we multiply, I'll call this like x for now. So here we have ax n1 plus bx n2, and this will be b2 minus a1. So like this, we derive the formula for the for k1 and k2. So basically k1 equal to ax and k2 equal to minus bx. So once we have like the a or the b, we can compute what is the x. So this we can compute it by using the initial formula we have here, this one. So x is equal to a1. Just rename this y. As you can see here, we have so the k1 is equal to a times y. And this is multiplied by the n1. Basically is equal to 3. And the y here is what? A2 minus A1 over the GCD of N1 and N2, all of this times N1. So this gives an expression for X. So yeah. But as we can notice, there are two important observations here. Here we assume that this number, like the A2 minus A1, is actually divisible by this GCD. So if it's not, then this equation is not solvable, because as we know, here from the Bezout's identity we have this. So any linear combination of n1 and n2 has to be a multiple of the GCD. So this equation, in order to be true, then A2 minus A1 has to be a multiple of the GCD. So if it's not a multiple, then it's these equations are not solvable. So the other way to say that they are multiple is to say that A is equivalent, A1 is equivalent to A2 mod GCD. So this condition we have to check before we actually compute the solution, and if it's not true, then we will not solve the problem. And if it's true, then we can just use it and compute this equation. And the second important observation is that we know that these A and B are not unique. But actually, so we can get all the possible A's and B's that would satisfy this equation. We'll find a good observation. And let's say here, so we have this as one solution of the Bezout's identity. So this is another number that is supposedly also another solution for the Bezout's identity. So we just add A here and B here, and we see what's the relation between the small a and the small b. So this, in order for this to be true, we come with the conclusion that an plus bm is equal to 0. And here we can divide n like by the, so the n and m by their greatest common divisors, which is the r. And this will be like that. So since this is co-prime with this, so here we must have that b, that this number divides the b. And also it has to go in the other way around. So this number has to divide the a. We can say that like the a is equal to some multiple in r, m over r. A and the b will be the negative multiple. So basically you can always keep increasing the a by this value k times, and we have to correspondingly decrease the b by this value k times r. So this gets all the possible solutions for the Bezout's identity. But we find that any of them would actually make the Chinese remainder theorem has still a unique solution. Because if we substitute these here in the we substitute this here in the equations that we have from here. It means I can increase this a by some value. You see. I'll just copy that here. Right, right. And as we said, we can make this is equal to 1, 2, 3, 4, 5, 6. So we'd end up having this. And this here is basically the old solution. 1, 2, 5, 5. So here, as you see, this is 0 plus this value, and this part is the LCM n1 and n2. And this is the value ik. So actually all the solution I can go into 0, not the LCM. Sorry, they can go into each other. So using this, it doesn't matter actually which solution from the Bezout's identity you use, so in order to solve this. So any of them would work. And actually there is indeed one solution that would be interesting in some of the cases. So here, in order to solve this, like when we were explaining the modular inverse, we could say that here so so here if we divide this equation by this BCD, so we end up having A n1 over R plus B n2 over R equal to 1. Means that modulo n2 over R, the A is a multiplicative inverse of this number. So basically this leads to the conclusion just writing down the code. So this leads to the conclusion that we have the A is equal to the n1 over R, or the multiplicative inverse, as we said, and n2 over R. So this is one of the solutions for the Buzut's identity. And this we can conclude by making as we said, using the Euler torsion function. One. So here we have this value to this power, so it will be, if we take it remainder into over R, so this is basically our A. So if we don't want to use the extended Euclidean algorithm, this is another way to compute. So yeah, so here's our formula to merge this one, and we already have two methods to get this value A. And this X it can be different, but all these X's are basically, so are all the same modulo N, where N is the LCM of N1 and N2. So putting this into code, here we put the R as the BCD of N1 and N2. And here we say that, so this is the A1 and A2, and this is the N1 and N2, and this is the A and N, which are the results. So this A here is our X here, this one. So this N, as we reach at the end, is equal to the LCM. That's one. So A is equal to A1 This is prior and then times a mod n 1. If we would like for now to just center on this one. And here we actually can use the standard PCB that we made earlier. Non entry D1D. Here I think we extended this huge further. Basically this is it. As I said, here we can make the A and so this part here just to get smallest positive value. So we can make an assertion. We could indeed get the right transformation. So here A of N1. A and A1 should be congruent of N1. And also A2 should be congruent of also return here Boolean like solvable or not, and 0 and false. Here it means we found a solution. Here it means the condition that we assumed is wrong, so there is no solution. Here we can try all the table as we used to do earlier. We'll do A1, 1, 2. Basically this is it. Here I put like n1 and n2, and then here I loop by all the possible modular values, so all the possible remainders for n1 and the same for n2. And in that case, we check if we can solve that. If so, then we do it. Then we print the solution. Otherwise, we say that this pair is unsolvable. Five compiles. So we have a bug here. Console. Now we run. Yeah, as we can see, so the Theorem 12 has these numbers, and 8.12 is these, and so on. So here the 1 corresponds to 1 and 1, 9 corresponds to 1 and 3, and it keeps going. So here are all the possible pairs here. So using the Chinese remainder theorem, so this construction makes the back transformation that we wanted earlier. So this now using from this we can go back to this transformation. Right now we can only do it for two equations, but it actually doesn't matter. We can easily generalize that into more equations. Simply just have this, like I would call a merge operation. So this solve, I would actually call it a merge. So it would merge two equations into one. So if we have like x1 and then x is congruent to ak and nk. And here to solve this, we can do it. We can solve the first I equations. So we say that x is congruent to a capital I mod and a capital I. And how do we govern the relation between AI and AI minus 1? So basically, when we try to solve AI minus 1 and I minus 1, so these two equations and this small I and small I, this will result into the pair AI and like A capital I and N capital I. So basically, this is how we extend it to solve k equations instead of just two equations. You can say here that it's 0. So the first A is 0 and the first N 0 is equal to 1. So basically this is it. So here we can go to the code and basically call this merge here. Here we have a vector of the A's and the vector of the ends. We can call it solved. Pause. So we solve A of I. Will take basically this would merge all the equations. So if we have here a third equation and this part, it's not compiled. So here I do it for 3 equations instead of just 2, and I use this generate method to solve all. And we have now it produces all the solvable pairs, or here in this case triples. We find all the numbers. So yeah, that's it. So this is basically the correspondence from, we have all the triples from here, we can get to here, or the opposite. We have here, we can get to here easily. So that's it for the Chinese remainder theorem. So one last point here. Because of this condition which we have here, so all the literature I found in the Chinese remainder theorem makes this assumption, or in all the ends before we even start to solve the equations. So here we can actually, so this is an extension to solve more equations, only if they could be solved. in the first place. So if they can't be solved, then we will just record that, but otherwise we'll solve them and we'll get the answer. We don't have to make a stronger assumption that they are already co-primes. Because if they are co-primes, then this is mod 1, so any numbers are equivalent mod 1. So they're even putting a stronger assumption. And also you'll see that here the LCM of N1 and N2 becomes the product, because also they have a GCD of 1, so it's expected like that. So that's it. So thanks for watching.